Hi, everybody. So what we're going to look at today is the idea of sketching log functions. And so we're going to look at what our base log functions are, talk about some properties, and then kind of introduce kind of a quick algorithm for us to be able to go through and sketch a log graph. So for us to just have a little reminder, you'll see at the top of the screen that log functions are the inverses of exponential functions. And so, if we remember everything about an exponential function, and we remember the concept of an inverse, then we should actually be able to create certain properties of a log graph, even though we've had very limited exposure to what that graph looks like. So what I'd like everyone to do right now is to take a look at the first column. And I'm going to put that column in blue because I'm going to keep everything that's exponential in blue. So in that first column, what I would like you to do is I'd like you to go through and fill in all the properties of an exponential graph that takes the form y equals a to the exponent x, where a is greater than 1. So fill in all those properties, for instance, for y equals 2 to the exponent x. I want you to pause the video. Go ahead. Okay, we're back. And so I'm hoping that we can just go through and confirm a couple things. First off, we can sub in any value for x. So our domain is x can be anything. Our range, regardless of what we sub in for x, the value of my base and calculated to that power is always going to be positive. When I sub in 0 for x, I know that my exponential functions always have a y-intercept of 1. I know that every exponential has a horizontal asymptote at y equals 0. And if my base is greater than 1, then I know that I have an increasing curve. So hopefully that just confirms everything that we jotted down. And what I would like you to do now is to pause the video and use what you know about inverses to go through and create all the properties for what the graph y equals log x from base a would look like if a was greater than 1. So let's pause the video now, give it a shot. Okay, we're back. And so hopefully when we take a look at the concept of inverse for us, we remember a number of things. We remember that that is a certain reflection of a graph, but we also remember how we come about finding an inverse, that we look at the function from a completely different perspective. So we interchange our x and our y. And so if my domain on my original curve is interchanged, then my range must match. If my y values on one graph get interchanged, then their x values must match. And so we have this relationship when we talk about inverse of those two things occurring. Now, maybe you didn't even use inverses to work your way through that, but instead you said, well, I know that whatever is inside my log must always be positive. Therefore, x is greater than 0. And if the inside is always positive, then I can calculate any one of those logs, and I know that I get a variety of answers. I can get positive values, I can get negative values, I can get 0. If we follow that inverse concept, then a y-intercept on one graph will then become an x-intercept on the other. My asymptote of y equals 0, that horizontal asymptote, would then become a vertical asymptote at x equals 0. This one may have been a little kind of jamming, and my guess would be this would be the one where we would make a mistake, even if we had a firm grasp on what an inverse was. That if I have an increasing curve on my exponential, I also have an increasing curve on my log graph. And we're going to see that in a moment to be able to clarify and maybe nail down as to why. Okay, now that we've got that, then let's jump through the next two just a little quicker. that we're good that we can have an exponential graph if we change the base to a value less than 1 but positive. That would then create a log graph with the same restriction on a. It must be positive and less than 1. So what I'd like you to do now is go ahead and fill in the exponential column for that change in function. Pause the video now. Okay, we're back. And so hopefully we said that will have no bearing on x. I can still sub in x or anything for x. Regardless of what I sub in, my y value will always be positive. I still have a y-intercept of 1. I still have a horizontal asymptote at y equals 0. But now I have a decreasing graph because the base of my power is less than 1. Now what I need everybody to do, pause the video again and see if you can come up with all the properties for your log graph. Okay, we should be back. And so if we follow that same sort of process, I notice that what's inside my graph must still be positive, or I interchange my x and my y. Then I can calculate anything as an outcome. I would then have a matching x-intercept at 1. I would have a vertical asymptote at x equals 0 and a decreasing function. Again, we're going to come back and we're going to nail down the idea of increasing, decreasing. Don't be alarmed if your initial thought was that they should switch. Okay, what I want to do then is I want to go through and produce the graphs of each one of these functions. So what you'll now see is I've given you a set of axes, and I'm just going to put a little wavy line down the middle just so we can keep the two graphs clear. On the left set of axes, what I'd like you to do is to go ahead and produce the blue curve. Let's produce the exponential graph. Once we're done producing that exponential graph, what I'd like you to do is to go ahead and produce the red logarithmic graph. So we're going to go through this together a little bit, and we should be able to move pretty quickly. We should all have a very good understanding of our exponential graph and what it looks like when we have a base that is bigger than 1. So, very quick sketch, there's our curve. Now, using the concept of an inverse, we may say that I know my inverse is a reflection in the line y equals x. And so if I reflected that blue graph, I could then create my red graph. Or we're taking a look at the properties of that graph and we're building it. So maybe we recognize that when we interchange, I will then have an asymptote as a property at x equals 0. My old y-intercept becomes an x-intercept at 1. And I now need an increasing curve. And so if I was to increase, I know that I always make a hard turn at my intercept. And so I get something like this. So hopefully our graphs match up, and all I want to do is just have a very, very quick discussion on why the red curve is an increasing graph. So a very quick understanding. If I was to take a look at the blue graph, then what I'm looking at is slope. And so what I want to examine then is the idea that before my y-intercept, my slope was very flat. So if I go back to grade 9 and I thought of it as 2 points, then my rise and my run would say that I need a lot of run to get a little rise. A lot of run to get a little rise. So if I was just to write down something crude and say a little bit of rise comes with a lot of run. So I just used big and small arrows in that case. Then when I go through and I find my inverse, That means interchange your x's and your y's. My large amount of run, which would be the change in x coordinates, would have to translate into a large amount of rise. My little bit of rise, when I take the inverse, would have to translate into a little bit of run. And so if I then look on the inverse graph, which is our red log graph, then before the x-intercept, I need a lot of rise and a little run. And so the idea of us then looking at a flat curve on its inverse becomes steep. We could then translate that into a steep curve must then become flat. Notice it doesn't mean that an increasing curve becomes a decreasing curve. The direction of my curve stays the same throughout an inverse. So hopefully that gives us a little bit to clarify, and we can then move on to that second type of function. So this is one where I'd like us to work through. First thing, I'd like you to pause the video and put down a quick sketch of your exponential graph if your base is less than 1. Pause the video now. Okay, we should be back. We should then know that we have a decreasing graph that would look something like that if we have a horizontal asymptote at y equals 0 and a y-intercept at 1. Okay, and now what I'd like everyone to do is to go ahead, pause the video, and sketch the red log graph. Okay, pause the video now. Okay, I just want to draw to your attention the number one mistake that we may have made. And I would bet that if we were sitting in class right now, I would have a bunch of people who would have something that would look like this. And I'd just like to draw to your attention how that green curve could not be the graph. However, a bunch of us have it. Take a look at what the x values would be for every point on that green curve. And we should be able to see you cannot have a negative in your x value inside the log. So clearly that's not your graph. So what was the error that we made? Well, our error that we made was that we all of a sudden reflected it in a different line. That if you want to create that inverse, then it is the reflection in the line y equals x. So we need to reflect that graph across. So let's use some of the properties as we reflect it. This y-intercept at 1 would become an x-intercept at 1. My horizontal asymptote at y equals 0 would become an a vertical asymptote at x equals 0. And now I need to go through and produce that graph. So this becomes kind of a weird one for us, and it's going to feel a little bit different. Because when I reflect it, it must be equidistant. Then that means that I need to take, for instance, this point on my blue graph and reflect it the same distance on the other side. This point way down here at the end of my blue arrow would get reflected all the way up, equidistant on the other side. More importantly, this flat stretch, when x is positive on my blue graph, must become a steep portion on my inverse. And then the steep portion must become a flat portion. And so hopefully we have a graph that looks like the red one, and we match up. Okay, what I want us to be able to do is to be able to work through both of those graphs. because in 1 day's time, we're going to start sketching these functions with all of our transformations included. So we want to be very, very good at knowing what each base graph looks like. Now, one case that we may encounter is the idea of ln, and I just want us to look back over the existence of ln. And so, when we take a peek at that, we remember that ln would be stated as lawn, like mow the lawn. We can use our calculator and we evaluate what y equals ln e to be, and we notice that that is 1. And so, again, formally, just to get down, even though we've discussed this before, what conclusion can you make about ln? I'm going to write something down that is terribly incorrect. It's that when we write log and we see ln, that we know that that's really a log base e. Now, where do we get into trouble and what would be incorrect? It happens to be that if you see a ln written in a problem, that there's a tendency at times for people to go, oh, okay, so, oh, yeah, so the base of ln is e. So, like, let me just sneak a little e in there, just so I remind myself of what. Never, ever, ever write down ln with a base e. Ln always has a base. It is a log base e, so do not ever write its base down. Okay, I think we have everything we need now. What I want to do is just kind of sum up some stuff. So what I'd like you to take a look at is just kind of two scenarios, and I've put them both in red. These are the two cases that you would be responsible for. And as I said earlier, we're about to start transforming all of these graphs. So we need to be able to get down a quick sketch of what that base graph looks like. So let's take a look at the left column. If you were to have a log graph, log x from base a base log graph, where that base is greater than 1, then one of the ideas that we want to tie to each other is what does the exponential do? Because I know that the log graph does the same thing. So, when you see that you have a base that is greater than 1, we know that the exponential graph increases. And therefore, the log graph does the same thing. And so, you'll notice, we know that that graph rises to the right. Now, if I can get you to take a look at the right column, where we now address a log graph with a different restriction, a different base. If I was to see a log graph that had a base that was less than 1, well, I know for my exponential graph, that means that I have a decreasing curve, and therefore my log graph would also have a decreasing curve. And that's why you see the term falls as we construct that function. So, if we can look back at that left column right now, then what we can do is see a very fast way for us to be able to construct a graph. So, if I had a quick set of axes, then if I had to construct a log graph where my base of that log was greater than 1, then I know that I have a graph that is going to have a vertical asymptote at x equals 0, and my graph is going to rise through that x-intercept of 1. Now, once I hit that x-intercept, I change curvature, and where I was steep, I become flat. Everybody take a look at the right column now. That if I was given a log graph where the base was less than 1, then I know that on an exponential graph, my base less than 1 means decreasing. That means that I have a log graph that must be decreasing. So I have my vertical asymptote. I must decrease through an x-intercept of 1 and then change curvature. So a very fast way for us to be able to get down a graph. So what I want to finish off with today then is just a quick chance for us to see how comfortable are we to produce y equals e to the x as a graph and then y equals ln x as a graph. So what I'd like everybody to do is just pause the video for a second and put down a very, very quick sketch of both. Okay, we're back. And so when I take a look at y equals e to the x, I know that that's like y equals 2 point something to the exponent x. So again, just remember, e is like 2 point something. If you want to go 2.71828, blah, 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 feel free. But if we remember, it's just 2 point something. That means that my base of my function is greater than 1. So my exponential graph rises or increases through a y-intercept of 1 and has my horizontal asymptote at y equals 0. We then take a look at my ln x function. Then I remember that ln is really log base e. And if my base is e, and e is 2 point something, then I have an increasing log graph. And so I have my vertical asymptote at x equals 0. 2 point something means an increasing curve, which means I need to increase through 1 and change curvature. And so there we go. Hopefully today was a good introduction to what log graphs are going to look like. And our next day, we're going to get into transforming them. So jump in and play around with your practice and nail down the key features of your base log graphs. Good luck.